This is bisectors in triangles, which is lesson 5.2, in your workbook on page 94. But while you're getting that ready, let me tell you about the standard. It's prove theorems about triangles, and our objective today is to develop some methods for applying theorems about triangles to find and prove various things about those triangles. In particular, find perpendicular bisectors, find angle bisectors, and use the properties of perpendicular bisectors and angle bisectors to establish congruency in some triangles. Here we go. First thing is the theorem. The perpendicular bisector theorem states that if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment, meaning, of course, that it is equally distant from each one of the ends of the segment. So let me show you what this looks like. This, of course, is a perpendicular bisector right here. You can tell because it is intersecting into 90-degree angles. And this line AB is the same distance. BD is the same distance as AD. So therefore, this is a perpendicular bisector by definition. And if we draw a line from CA to CB, CA to CB, because this is a perpendicular bisector, that means that this line is the same length as this line. We don't have to measure it. We don't have to do anything to it. We can prove it based on the perpendicular bisector theorem. Now, the converse of that theorem is that if a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of the segment. Moving on. The angle bisector theorem states that if a point is on the bisector of an angle, then it is equidistant from the sides of the angle. And if a point is in the interior of an angle, is equidistant from the sides of the angle, then it is on the angle bisector. And the distance from a point to a line is the length of the perpendicular segment from the point to the line. So a couple things. To do this, you have to have perpendicular lines going from the outside going in. If they're not perpendicular, this doesn't work. If you do, you know, if these are the same length as each other, then that makes this a bisector, an angle bisector, which then means that this angle is congruent to this angle. So D is 3 inches from AB and AC. They are both the same distance because they are both being met by the same thing at a perpendicular angle. Now, we want to apply the perpendicular bisector theorem. We got a map here of Washington, D.C. Here is the Lincoln Memorial. Over here is the Jefferson Memorial. Over here is the Capitol. And here is the White House. And this is not by mistake. This is one of the few cities in the country that was actually designed on a grid format, but that's neither here nor there. So here's a couple of things they want us to fill in. That the converse of the perpendicular bisector theorem states if a point is equidistant from the endpoints of a segment, then it's on the perpendicular bisector of the segment. And a point that is equidistant from the Lincoln Memorial and the Capitol must be on the perpendicular bisector. Now, to be clear on this, this last statement here bothers me. I don't think it's very, very clear. It kind of says to me that if a point is equidistant from both the Lincoln Memorial and the Capitol, that it's the perpendicular bisector. And clearly, these two things are not the same distance from each other. If you read that and it made sense to you, then fine. It doesn't make as much sense to me. What it means is that this point right here, that any point right here along the perpendicular bisector, so if I pick that point right there, if I have another point that is exactly the same length from there to there, then it is on the perpendicular bisector. That's what it means. All right, using the angle bisector theorem. So this isn't the perpendicular, but the angle bisector theorem. We want to find x, we want to find FB, we want to find FD in the diagram at right. So let's remind ourselves of what in the world the angle bisector theorem is. It states that any point on an angle bisector is equally distant to each side it is bisecting. So we have an angle bisector here. And so as we look at this, I can see right here, see the markings? That means that both of these angles are identical, that they are congruent. So that means that CF is an angle bisector, which therefore then means that BF is going to be congruent to DF. Or as they put it, FD is equal to FB. Works either way. So that means that all we have to do to solve this, well, all we have to do is we've got to do some algebra. So we got 2x plus 5 is equal to 7x minus 37, or 7x minus 37 is equal to 2x plus 5. So we're then going to add 37 to both sides. We get 42, and then we subtract 2x from both sides. We end up with 5x equals 42, and so therefore divide each side by 5. So we find out that x equals 8.4. So x is 8.4. That's one thing we wanted to find out. Also wanted to find out what FB is. So to find FB, you're going to do 2 times 8.4 plus 5, and that equals 21.8, and you can do it again if you want to, but it's going to also come out to 21.8 because both of these segments are the same. We've already said that. It's now time for you to do some quick check stuff in your own book on page 96. Why don't you do that, then come on back to the video when you are done. Here's the answers to the quick check. Use the information given in the diagram. So here's the diagram over here. CD is perpendicular, a perpendicular bisector to AB. We want to find CA. We want to find DB. Okay, well, since this is a perpendicular line here, and it is clearly bisecting it because this line right here is congruent to this line over here. This is a perpendicular bisector, so therefore the lines, the diagonal lines here, to A are going to be congruent. So that means that AC, or CA, is 6, and DB is going to be congruent to this one over here, so that one's 5 because it's a perpendicular bisector. All right, now this one is about this down here. So according to the diagram below, how far is K from EH? Seriously? How far is K from, it's right there, 10. And then this side over here is marked being congruent, so it is also 10. All right, then what can we conclude about EK? So EK. So there's no line there, but if there were a line drawing to EK. Well, since K is equally distant from both EH and ED, it's 10, we can conclude that EK is an angle bisector of DEH. All right, last two. Find the value of X. So we have here an angle bisector because we've got C, or from C to the edge here, is the same as from C to the edge here. So that makes that an angle bisector. So we can do the algebra here. This angle and this angle are equal to each other, so let's do that. And we end up with x equaling 20. So then the second question is to find DEH. So basically this angle here plus this angle here. So that's what I'm going to do. I'm going to do 2x plus x plus 20. There's a couple of different ways you could do it. That's just a good enough way. And then substitute in 20 for each one, and we end up with 40 plus 40, which equals 80. And so our objectives were to develop methods for applying theorems about triangles to find and prove various things about triangles. We found perpendicular bisectors, we found angle bisectors, and we used the properties of perpendicular bisectors and angle bisectors to establish congruency in triangles.